Okay, this is our final section of Chapter 5. We're going to talk about special types of right triangles. And we're going to be looking at 45, 45, 90 and 30, 60, 90. And we name these special right triangles based on the angle measures of the triangles. And really what they have are just special relationships between the sides of a triangle. So let's go ahead and write down what we know about 45, 45, 90 triangles. Okay, so when we have a triangle that is 45, 45, 90, which means, of course, one angle is your 90-degree angle, and then the other two would be 45 degrees. Remember from what we learned last try, this just makes sense. The first thing we know is that the two legs are congruent, which makes this an isosceles triangle. And then remember, the legs are the sides that are not the hypotenuse. So, we can call it L for leg, but those are the sides that are not the hypotenuse. And of course, the hypotenuse is across from the right angle, which makes that H, right? So, again, the legs are congruent, and that just makes sense because we know if a triangle has two congruent angles, it's going to be isosceles. But what's more important that's new today is that we can figure out the length of the hypotenuse or the leg given one or the other, because hypotenuse is equal to the length of the leg multiplied by the square root of 2. And these are just equations you're going to need to know, so put them on your notes, on your note card, memorize it, so that way you know what you're doing. But basically, this hypotenuse is equal to leg times square root 2. And that square root 2 will always be there. Okay? So we want to be able to use this to solve for, again, missing sides of a right triangle. And again, I could give you either the hypotenuse or the leg, and you should be able to solve it. Alright, so let's take a look at the example. We're going to find the value of x, and we want to give our answer in simplest radical form. So do you guys remember what simplest radical form means? That means you want to simplify your square root completely. That also means, I'm going to put an asterisk there, no square roots in the denominator. And we'll look at an, denominator. There you go. And we'll look at an example of how to get that out of the denominator. Alright? So first things first, look at what you're looking for. Alright? I'm looking for x, and what is x? And, my bad, there's a right, let's pretend this was already there. I forgot to draw on that right angle. Okay, so now let's back up and pretend we just saw this problem. Okay, so start with what you're looking for. I'm looking for x. It is across from that right angle, which makes this which side? This is the hypotenuse. Oh my gosh. So this will be a hypotenuse, right? Which is my longest side, and then I know, again, the other two sides are going to be the legs. Now what I can do is I can always start with the theorem and say, well, what do I know about the hypotenuse and the leg, right? Well, I know the hypotenuse, I'll just use h for hypotenuse. H is equal to leg times square root 2. And again, that's always going to be true with the 45, 45, 90 triangle. Alright, so now all we have to do is plug in our values and go through and solve. So I know hypotenuse is x, which is what I'm looking for. The leg is 2 square root 2. And I want to multiply that to the existing square root 2. Okay, and don't forget your algebra, right? Square root times the square root is just the square root of the two radicands put together. So 2 times 2 inside 1 square root. So x is equal to 2 times the square root of 4. So x is 2 times 2. So x is 4. Alright, nice and simple. Okay, let's take a look at the next example, and I promised you we'd look at one where we'd end up having to deal with square roots in the denominator. Alright, so once again, let's just pretend I didn't forget to draw on the right angle. There we go. And let's, again, identify what you're trying to find and use that to help us with the problem. Okay, so if you look at the triangle, sometimes it helps. Again, we know it's going to be a 45, 45, 90 triangle. So I know my equation is definitely going to be hypotenuse equals leg times the square root of 2, right? So now just go through and identify what is what. So 6 is my hypotenuse, because that's across from the right angle. And then x is going to be a leg. And remember, your two legs are congruent in this case, so we only need to find just an x, and we're good. Okay? So go through now and plug in your values. Alright, hypotenuse is 6. Leg this time is the x, and that square root of 2 stays in my formula. Alright, so do your inverse operations. I'm going to divide by the square root of 2. And remember what I said earlier when I said simplest radical form? That not only means to simplify all of your square roots, but also, I don't want this in the denominator. Right? So your question might be, well, how do I get rid of it? Get rid of the square roots in the denominator simply by multiplying both the denominator and the numerator by the square root of 2. So remember, square root of 2 divided by square root of 2 is just another way of writing 1. But this way, what we do is we get rid of the square root in the denominator, which is called rationalizing the denominator. Okay? So then 6 times the square root of 2 doesn't really go anywhere. But remember, square root of 2 times square root of 2 is actually the square root of 2 times 2. So let me bring this up over here. We get 6 square root 2 over square root of 4. And I know the square root of 4, oops, sorry about that. And then I know the square root of 4 is 2. And look, this creates an expression I can continue simplifying. So we rationalize the denominator not only because we don't like square roots in the denominator, but sometimes it also helps us simplify the answer even further. So I know 6 divided by 2 is 3, so I'm just reducing that fraction. So x is equal to 3 square root 2. And done. Alright? So those are 45, 45, 90 triangles. We've also got another special right triangle called 30, 60, 90. So obviously 30, 60, 90 refers to the angle measures. So we've got the 90-degree angle, obviously, and then we've got the smaller angle, which will be 30, and the larger angle, which would be 60. And then we're going to talk about the relationship between the three sides, and this time, the acute angles are not congruent, so we don't have an isosceles triangle. This is going to be scaling, and so we want to talk about 3 different sides. So we still have the hypotenuse, and we have 2 different legs, and the legs, I call them the short leg, so I use SL for short leg. And I know the book uses S, but I use SL, so you can use whatever you like to help you label that. And then this longer leg, I call long leg, and I believe the book calls it just L. But I'm going to abbreviate it as LL. And then, of course, we've got our hypotenuse, which we'll call H, and that's, again, always across from the right angle. Now let's type out the relationship, or write down the relationship in the theorem. Okay, so once again, there are 2 things we know from this theorem, but this time again, it is a scaling triangle because of, again, the angles. None of them are going to be the same. So the 2 things we know are, 1, the hypotenuse is twice the length of that short leg. Okay, so again, H for hypotenuse, it's always going to be twice the short leg, which, again, I'm using SL. Here you can use S, like the book, if you'd like. Okay, so that's the first thing we know. The second thing we know, if we have a 30, 60, 90 triangle, is that the long leg is equal to the short leg times the square root of 3. So 2 different equations to know here, and sometimes we need to put them both together to come up with the answer to a problem. So again, the long leg is equal to the length of the short leg times the square root of 3. And that square root of 3 is always going to be there. So notice there's both square roots for 45, 45, 90 and 30, 60, 90. And if you get confused between 1 to use square root of 3 and 1 to use square root of 2, I always think 45, 45, 90 is the square root of 2 because you've got 2 of the same sides, right? 2 of the same angles. 2 numbers are the same. 30, 60, 90, all 3 are different, so it's the square root of 3. But you're going to want to know that difference. Okay? Let's go ahead and do some examples and finish off today's notes. Alright, example 2. Find the value of x, again, simplest radical form, no square roots in the denominator. And, oops, we're going to also write and y because I forgot to adjust my notes for this video. Okay, so what I normally do is I, again, go through and label everything I know. So, and oops, I made so many errors before I made this video. Okay, hopefully on yours I've already corrected these, but that 90-degree angle working parent is already there. But let's go ahead and label the sides. So remember, across from the right angle is always the hypotenuse. So that one is super simple to start off with. So h is equal to 22, right? And then we've got two sides. We've got the short leg and we've got the long leg. How do you know which one's which? Well, remember back from a couple sections ago, the longer side is across from the longer angle, which means the shorter side is across from the shorter angle. So if this angle is 60, that means this tiny angle over here has got to be 30. So across from the 30 is going to be the short leg, right? Which then means the angle across from that 60 is going to be the long leg. Alright, so you might be wondering, wait, how do I find x and y? What are my equations? Well, go back to the theorem. And remember, we had two equations from the theorem. We knew that the hypotenuse is equal to 2 times the short leg. Alright, and we also know that the long leg is equal to the short leg times the square root of 3. Okay? Now what I like to do is I like to write both equations down, and then I'm going to plug in what I know, and then I should be able to see very clearly which equation I can solve. So let's go ahead and plug in our values. And there we go. So looking at these two equations that I have here in red, 22 equals 2y and x equals y square root 3, hopefully you're seeing one equation is actually the equation we can solve first. Which one is it? It's obviously the one that only has one variable. So let's go ahead and solve for y first. And once I know y, I can bring it over here to plug it in to solve for x. So I'm just going to divide, oops. Oh, I don't know what I just did there. Let's undo. There you go. Oh, there you go. So let's go ahead and divide both sides by 2. And I'm going to know y is equal, oops. Y is equal to 11. Okay, and again, I can go ahead and plug that in here to solve for x. So x is going to equal 11 times the square root of 3. So that is it. All right, now let's take a look at example 2b, because sometimes our problems may not be as straightforward. So it all depends on what numbers you're given. All right, so once again, let's pretend I didn't forget to draw on this right angle. And you should be able to figure out which one's your long leg, your short leg, and your hypotenuse. Alright, so hopefully you've recognized hypotenuse is x, short leg is y, long leg is 15. And once again, set up your two equations and then see which one you can solve first. So remember, we know that the hypotenuse is equal to twice the short leg. We know that the long leg is equal to the short leg times the square root of 3. Okay, so plug them in. So x equals 2y 15 equals y square root 3. Which one can I solve first, the right or the left? Well, the right, because again, this is the one that has one variable. So let's go ahead and divide both sides by square root 3 to get y. And remember, simplest radical form means no square roots in the denominator. So what should I do to get rid of that square root of 3? Well, I'm going to multiply both the numerator and the denominator by that square root of 3. Because remember, square root of 3 over square root of 3 is basically 1, but this is what helps me get rid of that square root in the bottom. So 15 square root 3 over the square root of 3 times 3. So y is equal to 15 times square root of 3 over square root of 9. So y is equal to 15 square root 3 over 3. And then reduce if you can. So y is equal to 5 square root 3. Right? Definitely let me know if you have some questions with this rationalizing the denominator, because that is something I expect you guys to do. Alright? So once we have what y equals, let's just plug it in. So x is going to equal 2 times 5 square root 3. And super simple here, just multiply the two numbers outside of the square root. So x is 10 square root 3. And we're done. Okay? Awesome. So one final example, you may or may not realize what you can do with equilateral triangles. All right, last example. An ornamental pin is in the shape of an equilateral triangle. All right, the length across each side is 6 centimeters, so that means this entire length is 6 centimeters, right? And since it's equilateral, all three sides are the same. Awesome. And what we want to do is we want to fasten the pin, basically, right, the fastener for this pin, along this length AB. So let's go ahead and call that whatever you want. I'm going to call it X. Okay? Now, how do I do this? You might say, oh, Miss Huang, it's impossible. I don't know how to do this. Well, you've got two options. All right? One, if we're fastening this length straight down the side, this is a right triangle. So what you can do is you can remember, if this entire side is 6, cutting that in half, each of these would be 3 centimeters. So here, Pythagorean theorem works very well. However, depending on the way it's set up, you may or may not be able to use the Pythagorean theorem. So let me also show you something else you can do with equilateral triangles. By cutting this in half, not only do we know this is a 3 centimeter length, we also know now that half the triangle is a 30, 60, 90 triangle. Now, does anyone remember, do you guys remember why it turns into a 30, 60, 90 triangle? Well, what do you know about each angle in an equilateral triangle? All the angles are the same, so they're all 60 degrees. Okay? So that means this is 60 cut in half, which is 30. This is 6 centimeters, this is 3 centimeters, and this is my long leg. So instead of doing the Pythagorean theorem and doing a squared plus b squared equals c squared and having to deal with the square root, all I have to do here is remember, long leg is equal to how much of the short leg? Short leg times the square root of 3. And which one's the short leg? Across from 30, which is the 3 centimeters. So long leg is actually just 3 square root 3 centimeters. And that's it. So for me, that actually took a lot less work than having to do the Pythagorean theorem. But again, depending on you and how you process, maybe Pythagorean theorem is a little easier. All right, but that is it. This is really important. You want to make sure you know it, not just for this test, but we're going to come back to it again and again when we have right triangles. We're going to have a chapter all on right triangles. And for those of you moving on to pre-calc, this will come back in pre-calc as well. All right, I will see you guys in class. Please come back with questions.